Professor Bernd Grambo. At present, he is distinguished professor at Subatec in France, and he has a long international experience in the field of radiochemistry. He studied in the Freie University of Berlin, and then he worked in the Hahn-Meitner Institute, and then in Forschungszentrum Karlsruhe. Then he moved to the States and worked in Northwest Pacific National Laboratory. And from 1998, he is a professor at the University of Nantes in France. He has worked in this field between chemistry and physics, which is radiochemistry, which is a very important field concerning many aspects, in particular nuclear contamination, nuclear waste, and he has worked in treatment of nuclear waste, among other subjects, many subjects of radioactivity. And for this work, he has received to my knowledge, at least two academic distinction, the Van Péchet, the Grand Prix Van Péchet, the French Academy of Science, and then he has been named Chevalier de l'Ordre Académique de Palme Académique in France also. He has a well-known reputation in this field, and he has also published a book about the treatment of nuclear waste. It is in French only, Le nucléaire au fil du temps. And I think that just to say that he is a well-known person in this field, and among his research, he has studied the way to have nuclear waste in such a way that will not leak in a long geological period of at least 12,000 years or so. Then I leave you with Professor Grambo, that will explain better than me.
Okay, muchas gracias. Buenos días a todos, pero no soy muy bien en castellano y hablar inglés es mejor. So I'm speaking now on scientific research addressing nuclear legacy. What is nuclear legacy? What we understand by this? We have territories contaminated by nuclear accidents. There's, for example, also for the Hanford sites in the United States, we have about 63 single-shell tanks which were produced, and some were leaking. And then in Chernobyl, in Mayak, in Winske, in Chernobyl, Fukushima, there were accidents which had led to large contaminated areas. And there's also contamination from mining areas, from uranium mining and so on. There's disposed radioactive residues, which somehow faced a paradigm shift because, for example, in the 50s, it was quite normal to put the nuclear waste in the ocean. And now, today, this is not so much normal anymore, and so people think of getting out what previously was a solution, today becomes a problem. And so we are, at many of these areas, we have the same situation. We had the acid salt mine where there was disposal in the 70s of radioactive waste. It was considered one of the most advanced technologies at the time. And today people think to take it out because it was not right done. There's also a learning phase how to deal with all of this waste. And but taking this waste out from such a site would cost about 30 billion euros, and then where to put it. There's lots of other questions which come to this. Now, there is decommissioning needs for nuclear facilities, including fuel debris management of accidental facilities. There's liquid waste arising for treatment or solid waste waiting for disposal. And not to forget also positive legacy. Positive legacy for me is also that in some ways the energy which we have gained from nuclear is something, of course, this avoided us to produce lots of CO2 into the atmosphere, so we're still producing more each day, but we would have produced even more if we would have not nuclear. But to me, the positive legacy is for us, is for our generations, but the negative is for our children. So we leave this somehow to them to solve our problems, so we get the benefits, they get the problems. Then I'm talking more on these negative aspects. So all of this started in 1943 in when the nuclear reactor, the first nuclear reactor worldwide, get critical in Chicago Pile 1. This wasn't the Manhattan Project. And since then, nuclear waste was produced, and since then, the solution has not been achieved. So here you see a stone which was put in the 70s to say don't dig down because there is some waste in the ground. There are areas and buildings which were contaminated and so on, which had to be taken away and so on. For some past major nuclear accidents, I just mentioned Chernobyl and Fukushima. In Chernobyl, there was a uranium graphite reactor with a core explosion leading to a release of about 1.8 million terabecquerel of iodine-131 and contaminated about 10,000 square meters of territory with more than 500 kilobecquerel per square meters and so on. And some hundreds of emergency workers get acute radiation syndromes, and about 300,000 people were evacuated, and still 270,000 people living in contaminated areas. Thyroid doses could be very high, up to 1 grade, and also the problem was always that the information was somehow restricted or too late, and there are quite a number of psychological problems associated. I remember from 3 Mile Island accident in the US, this number of smoking was increasing a lot, and medical use was increasing. People were having also fear to this, so this has also strong impacts. Now, in Fukushima, this was 2011. 3 reactor core melted when there was earthquakes and the tsunami which was following. The earthquake did not destroy the reactors, but the reactors were destroyed then by the tsunami, and they were not sufficiently prepared for. And again, a large area contaminated. The contaminated area is maybe 10 times lower or so for the same degree of contamination as in Fukushima, as in Chernobyl. Again, there was about 150,000 people evacuated. Still right now, I think it's some 100,000 which have been lost. The number of emergency workers, they were better protected than before in Chernobyl and so on. But also there we have psychosocial issues, poor risk communication, difficulty to communicate with the public in this area. You see this here in the zones which in Fukushima has been fixed there on, I can use this, I think. You see here the inner circle of 20 kilometers. This was the first one to evacuate. Then there was sort of the second one, about 30 kilometers. When people realized that, attention, there's some wind and the radioactivity goes more to the northeast, northwest, and from the center here where there was the explosion, and not evenly distributed. So essentially you could have evacuation orders going from this place to an even more contaminated area, which happens in at least in one case where these things has been done. So now, after some time, so the new evacuation order was more around this area, and the green area, the blue area was already in 2016 lifted. The green area should be lifted in about the year 2016, and you see 2018, it's all blue. That means this is gone, and essentially today it's this inner circle which still has rather high radioactivity and which may have radioactivity for a long period of time. In this diagram you see the same again here on the left, but you see some impacts of doses. What is here is the average dose in these areas, like in Kavochi village, from total exposure, which is external radiation, which is less than 1 millisievert. You have the radioactivity which you eat, the ingestion, and then you have the radioactivity which you inhale, which you take in with the gas. And essentially, most of the radioactivity, the logarithmic scale, is in the area of external exposure by the cesium on the soils and so on. So, and this goes only very, very slowly down to this radioactive decay curve, but it's as well somehow the fact that radioactivity goes into the deeper soils with time. But then you can calculate from this additional cancer risk. So the average cancer risk in this area for a baby, for example, of 2 years, 10 years, or 20 years is given here in these 3 blocks of data. And you see here for the lifetime exposure, this corresponds to some 40, 30 or so millisieverts. So the sum of these curves over your whole life, this was for 1 year, this is for the whole life, and the exposure of the woman or the man, you could get about 1 millisievert out of this, and now you get 42 millisieverts somehow as maximum in these villages, but it's not in the center areas. That would be quite higher, but in this area, which was where the evacuation orders were lifted, was about 1 millisievert, which you 40 millisievert, which you get. But if you put this now in cancer risk, there's 1 out of 100 person which may die from a cancer maybe later in his life and so on. Of course, this needs to be compared with the background risk of cancer in the same region, which is about 30 to 40 times higher. So the risk of dying from cancer from non-radiative sources is much higher, of course, of that dying from the radiation sources. These are some photographs just to show this, the exclusion zone, the blocking here of people coming in, the radioactivity measured from external radiation, but also we're taking samples there to looking at what's inside of the radioactivity and so on. And you see some readings here in the area in terms of microsievert per hour. Now, nuclear legacy is not only contaminated area, it is also nuclear reactors, which at some time stopped to be useful, and so they will have to dismantle. So we see here the number of reactors which are under construction is about 58 right now, particularly in China and some also in India and so on, Russia. Then you have the number of reactors in operation, about 10 times more. And then you have the number under deconstruction shutdown. There's 160 already under shutdown. And I put this small insert so that you see how it is in Spain. There's 3 reactors shut down. This is here somewhere. It's in the world for Spain as well. So you see there's and the years, Vandelos was already shut down in 1990, and it's the base is still there, and it's someplace and not removed. And then there's growing decommissioning needs over time, as you see here. This is maybe for 50 years. You see what kind of quantity comes out. And think if you do all of this together, you come to some kind of $500 billion which you would have to spend to get all of this somewhat. So it's a huge business. Somehow it's a huge investment which one won't do, but very difficult to assess because no industry is capable to waiting for its money maybe 10, 20 years because there's a stop of program, because it can start again. There's lots of licensing problems and so on. You see that legacy waste concerns not only the reactors, it concerns also use, for example, for the UP1, which is a reprocessing plant which is shut down in the south of France, Marcoule area. And the different types of waste. You have some 3,000 glass canisters with high radioactive matter. You have about 1,000 tons of magnesium clads, very high radioactive, and so on. Some 26,000 tons and so on of waste from active area. You see some pictures of this. I will not go very much into detail, but you understand the magnitude of the problem. Now, here is the waste. This is a recent presentation of the IAEA worldwide. The distribution of the waste, so we classify this as very low level waste, and here this is intermediate, very low activity, intermediate activity, and high activity. And we see decommissioning waste is very strong in this area, but the most is a very low activity. Yes, this is very much, but it could also include hospital waste and other things here. And the high level waste in cubic meters is much, much lower than the rest. And in decommissioning, the high level waste does not take very much part in this. So when the reactor is shut down, the nuclear fuel which may have been in the reactor needs to be safely stored. For example, there's wet storage, there's dry storage, and for example in Spain as well, both techniques are used at different reactor sites and so on, waiting for some kind of final disposal. But that's some kind of, for final disposal, fundamental questions. What you do see here is the evolution of the radioactivity as a function of time, and you need to go to some millions of years. You see, for example, plutonium activity, and that's for the 1 year of French production of radioactivity expressed in toxicity units, 10 to the 8 would be in kilosievert, 1 millisievert, so it would be 1 million times lower than these axes, and then this value, 1 million times lower than this value. That's what is a public allowance in the European Commission. We are here about million times 8, so we have 10 to the 14 times lower, higher in risk. Somehow it's a risk unit somehow to what is allowed in the European Union for ingestion. Principle, the toxicity is dominated by plutonium, by cesium, and by other. And somehow, some of these nuclear fuel disposal places takes about a few minutes if you are close to the nuclear fuel, burnt nuclear fuel, to get the lethal dose. So these things are very dangerous. They need to be protected in sealed sources, and access needs to be controlled. It's impossible to have these open. So that's somehow the idea, to say how we can find a place where it is isolated and where we don't need to ship it from one place to the next, and somehow the only way people came up with is geological disposal. There was some time people were thinking, why not transmuting this waste? So there was, particularly the nuclear physics community, made themselves very, very eager to find solutions for putting this waste in a new reactor, like a hybrid reactor or a fast breeder reactor or something like this, and burning some of the fuel. And you can somehow reduce the actinide inventory, and you see the actinides are rather important. But what you cannot remove a lot is the fission product, and in the long run, it's them which are somehow dominating the dose. In particular, iodine is very important. You do not destroy this with transmutation. So this means that for the long run, you still need a solution. Even if you transmute some of the actinides, there's still a reason to have a nuclear waste repository for the rest. And as far as I know about safety analysis of nuclear waste repositories, they are in the US maybe, but in Europe they're never controlled by actinides because they're very immobile in the geochemical environment of and so sufficient products become more important. But the question is, how can we be sure that what we dispose of really stays where we have put it there? And there's also a question of trust. How can we get confidence in this area. So this is not only a scientific question, it's also sociology or political questions, how to deal with this waste, and society must agree upon, not scientists, because scientists have, it's easy for them to agree, but they will die, and later on the waste is still there, and people get new solutions, and so on. There needs to be consensus in society in these areas. So the idea of a geological disposal, maybe about 500 meters deep. So you have here the disposed waste. Then you have large rock bases, and essentially you need to make sure that the waste which you put in here takes some million years to move up. And now the mass transfer of not only radioactive matter, also of natural substances across such a distance could be extremely low, and some of this waters, groundwaters, which has been probed in these areas of nuclear waste disposal sites, they have found that the age of the waters is in the millions of years range, and so sometimes even the hundreds of millions of years range. So there's some probability that we can assume that the radioactivity will stay at the place if there's no groundwater going up. There may be volcanism, but then you can put it in an area where there is no volcano. Then there may be earthquakes, and you can try to find an area where there's less impact, or, for example, in a clay repository, where impacts of earthquakes can somehow be mitigated. There's an ethical imperative about this, and that's why I say it's a small sociological question rather than a scientific one. And many people say, why not leaving things there? Let the next generation solve. We have no solution right now. They're opposed to a solution of geological disposal without offering another solution. So the other solution is leave things where they are. And leave things where they are is, to my feeling, also a problem for future generations. There's an important transfer of radiological reliability to future generations. This waste, which is on surface sites, could be vulnerable to international crisis. Now we have in Europe, we had the last war about 60 years ago, and this may not be the last one. And people come more and more to nationalist ways of thinking, the probability of these types of conflict would more or less rise and not fall. So I would, and it's the only time in history where there was no war. So I have difficult to imagine that this will not be new wars in Europe in the future. So well, these areas of contamination could be the larger vulnerable areas. This is a high security risk as well, because many of the storage places, I don't know how it's in Spain, but in the US and other places are close to big cities and so on. And so one needs a long-term isolation. Long-term, the only thing is a passive barrier system for disposal, where we don't need to look at it. Of course, you can say if it's passive barrier, you put the waste someplace and you forget about it. It's like dumping in the ocean. This is just, you lose your responsibility, which is somehow true. But in the opposite sense, to say we do nothing, we leave things on ground, maybe even worse. And we cannot guarantee. Our generation may have the responsibility for this waste, but our generation cannot assure that the next generation or the next generation will keep up the nuclear education sufficiently high that people will know what is the risk of this waste. So the knowledge will disappear or can disappear maybe. And there are quite a number of risk questions according to this, where we need to make sure by passive system, and we cannot rely on this from generation to generation. And here we need to look for thousands of generations. Thousands of generations is just 40,000 years. Yeah? And how to transfer information over thousands of generations is impossible even in one generation. Yeah? And so then to do this over thousands is very complicated. So, but it's a subject of debate since many times between scientists and society. There was a strong engagement of the European Commission since the 80s And most geoscience nuclear engineers believe that disposal is somehow the best solution. But there's a problem of trust, and nowhere in science there is more a dispute on this area. And when I started in this area 40 years ago, this was already a question, and today it is still not solved. So I think it's a thing where the positions are relatively fixed, and that's why I think we need in this area to have consensus. We need to have discussions. We need to avoid that our solutions which we propose are then taken forward. There's also in this area, compared to other risks, like for example car accidents or AIDS or so, there is less trust in the public with respect to their governments. So, the government in car accidents, they say, okay, they do what they can. Of course, there will be car accidents, and we reduce the speed limit, we do things to solve it. And the citizen would somehow think they do what they can. In the nuclear area, people, at least in France, I don't know how it's in Spain, by different retail pays, it's not so different, that people also would have fear and would believe that the government is not saying the truth, and that nobody wants to live close to a nuclear waste disposal site, and about 16% of the population in France have no problem living close to a nuclear reactor. But nobody wants to live too close to a nuclear waste disposal site. But it's the idea of that nuclear waste is something like other type of waste. You just dump things, and we later on contaminate. People believe that there's coming a large catastrophe from the nuclear waste. And on the other hand, the real reactor catastrophes, like I've shown at the beginning in Fukushima, they come from nuclear reactors. They do not come from nuclear waste disposal sites. So there's really a mismatch between public perception and where I would, as a scientist, believe that there's a risk. But as I say, risk is not only scientific criteria. Risk is a societal one. Risk is something we negotiate. What is risk? What's not risk? How is so? The scientist can present risk in the number of deaths per unit of events and so on, and probability times damage. That's risk from scientist perspective, but from society perspective, it's also the fears, it's also the stigmatization of territories. I cannot sell anymore my vegetables and my champagne and so on. So there's lots of other things going into risks than just this probability times damage. So in Spain, you have disposal site for low-level waste since '61 in El Cabril, which stores quite a number of waste since many time. The high-level waste is in Spain. They have an open fuel cycle. That means there's no reprocessing provision. The Parliament has said we should have a central nuclear storage facility, and the government in 2009 they asked for volunteers to host such a central storage site. There was, I think, 4 sites which were selected, and then finally Villa de Canes was selected, and which gained after some time the accrédité was the CSN, the Consejo de Seguridad Nuclear, accepted this and says this is possible, but the licensing process is still ongoing. This should be for some 60 years, and after that there should be found a solution. Again, you should ship it to some place, and later on this would not be the final one, then you would ship it again. But there is, of course, an advantage shipping it to one central place compared to having it in all different reactors distributed. May be an advantage. But as you see, we need to go somehow for a final solution at some place. And the project is not exempt from the degree of uncertainty. There's still opposition by some regional authorities and so on. Where's the radioactive waste? So it is somewhat in various areas. It's in the US, in Europe, and in Japan, quite a bit. Just also a recent map of the IAEA. I made some general remarks, starting from World War II, in a today quite different economic environmental, historical, and cultural context, the environmental footprint of nuclear legacy has always increased, as has the burden for future generations to clean it up. There's no clearly or generally shared roadmap how to reduce this burden. The number of non-solved problems continues to rise. Nuclear legacy accumulation is complex, typically characterized by substantial industrial investment in nuclear area as well as in social, ecological and environmental change with radiological consequences which are sometimes difficult to forecast. The complication is also in the absence of a culture of radiological risk among various stakeholders. What is really this risk is not really so clear, and there's a strong polarization between public opinion on the one hand and the governments which try to solve this solution. So to me it's planetary challenge. Since we work on this since 70 years, and I'm pretty much sure for the next 30 years, to 70 years, this will continue. We will not find the solution. It's unprecedented complex, the handling of the radioactivity, and the strong coupling of large-scale contamination, climate, and geochemical science. It's a planetary issue because many tens of thousands of people were evacuated and so on, and square meters are not anymore used, which influences also prosperity. The costs are astronomical, as I may show in the next slide. Here, this is from the United States Department of Energy, just the projected cost for cleaning up Hanford as the more defense-based part of the nuclear program of the US. It means those which make the bombs. And it's in the range of 7 billion per year until the next 20 years about, and then it will go down, and the total is about 300 or so million of dollars to be spent. And what's interesting is this all engineering work, shuffling things from one place to the next, and from that place again to a third place, and so on. Now, there are about, I would say, 5,000 people involved just to do this cleanup. So it's also business, it's also work of people to get their revenue from, and their whole life they spent on these things to clean things up of other people. So it's really a very large effort, and it's the SEAB task force recommended, I forgot what this actually means, this abbreviation. They analyzed this program of the US Department of Energy, and they made recommendation to the Secretary of State, and they say essentially what you have here is less than 1% is in research. You should do more in research to try to reduce some of this burden faster by understanding better what you're really doing, and not just putting engineering-wise from one place to the other. Fukushima is similar, yeah? So there's also in the 10 billion per year of spending. Now, I will just use an example. This Rocky Flats is a plutonium facility in the United States, which was shut down after a plutonium fire. Plutonium is metal, and the metal has powder, and the powder can burn metal powder. And so there was lots of contamination. There was 21 tons of weapon-grade nuclear materials, and so on and so on. I will not go through all the list, but just to mention here, the US building 771 was considered at the time the most dangerous building in the United States, and they did a prediction that the cleanup would cost about $36 billion, and dollars, of course, and it would take about 70 years. And what could science do in this area? How can science help? Now, what they did is they identified the contamination. They found out the real risk is not water contamination by plutonium, but air pollution by plutonium particles. And so they built a tent on all of this, and they could solve this in about 10 years. So that was about 60 years earlier than they thought of. It's probably one of the only reasons why things get faster than they were projected initially. But it's a good example how you can use science, because they use synchrotron radiation, for example, for identifying, characterizing these particles of plutonium and showing that the mechanism by which they are transported, so that they then could build a strategy somehow to clean it up. I should also say this is not a final cleanup, so it's somehow used for you can hunting there in this area, but you cannot have children playgrounds there, so it's not for use for everything, neither. An example of Fukushima, where you need lots of research. Fukushima was contaminated, essentially forest area. There's a large area with lots of forests there, and forests are almost entirely impossible to decontaminate them, because it's on the trees, it's in the ground, and so on. So they built somehow an understanding of the different processes, like soil loss by erosion or resedimentation, the transfer of cesium into the forest ecosystems, to the rivers, and then to human beings or animals and so on. How is this ongoing, all the different steps to understand. So I think one learns quite a bit how this transfer occurs in nature. And here's just an example of the cesium behavior. The total cesium from these two rivers is about, I think, 300,000 or so terabecquerel of cesium. And there's less than about 1 terabecquerel which goes to the, or about 1 terabecquerel which goes to the ocean per year. Now, this transfer processes had been characterized all over, and the good thing is somehow there's still, I don't know, 1 terabecquerel may be considered large or small. I would not comment on this, but it's interesting that 99.9% stays in place. That means that the radioactivity will not get out, which has the good thing that it will not so much contaminate the environment, but it has a bad thing that it will continue to be there to contaminate everybody which enters the forest, and for the next 1,000 years, not just for the next 10 days or 10 years. And so this will be a long-lasting issue, what to do with all of these things. So one thing we're working a little bit with Japanese scientists in this area. I have also a small group in Japan on this. So we have here the biogeochemical cycle of mushroom. Mushroom take up lots of cesium, and then you need to understand how the radioactivity goes from the mineral by some metabolite to the mushroom, and how from the mushroom this goes back to the soil by the dead mushroom, and so on and so on. But it's a very tedious effort, and many questions are not known. And there's also a missing link between the radioactivity in the soils and the different compartment of the soil, to the plants and to the minerals and so on, and comparing this, which is still not very good understood, with the transfer to the food chain, so that people eat these plants, and how this gets then into the human body. And there again, the cesium is redistributed. I just put here a schema in the human body, between the liver and between the different parts of the human body. It's very complicated skin. And between these two, there's too little interaction. For example, people have measured by children, about 100,000 children, they have put in Japan on the whole body counter, and they have shown that there's about 10 times less cesium in the human body in Japan as compared to the cesium in Chernobyl. And there's no really explanation, there's no really research ongoing how this could happen and how this transfer from the soil is ongoing. This may be food habits, maybe what people eat is different, they may eat rice from different regions, not from the contaminated areas, and so on and so on. I will not go into detail and speculation. The scale of the project is relatively large, that you do have the questions of multiple coupling of transfer of cesium and potassium, for example, in a single plant or tree. And we still today, it's just a single transfer like this. We do not understand. We are not able to predict how, if there's some cesium in the water, how would it go to the different plant parts, and how is the effect of light, of temperature, of cesium. what is the impact of plant physiology, and so on. So I think already at that level we're missing some general metabolic flux models and so on to describe all of this. So I think if only a fraction of the money would have spent in this area that one spends to find out the boson of Higgs, I think one would be very, very far advanced, which is also a question where society puts its efforts. So it's more interested in the boson of Higgs than in these things. It's fine, I'm not against it. And I think it's very important to know the standard theory of physics, certainly, but I think it's an important issue. So what can you do? You can do also, for example, just as an illustration, use the ICP-MS laser ablation. You can increase the distribution of radioactivity for different elements. Potassium is, for example, here, which would be an analog to cesium. You see how things can be done. In our laboratory, we look, for example, for tree rings, for uranium distribution in these tree rings. Here you see some images. And you can as well all use as chemists, we are always interested in oxidation states. That means the different chemical elements behave entirely different, whether they have technetium-4 or technetium-7. That means whether they have less or more electrons in their shell. Now, there's a question of scale. You go from locals, from more scale of meters and so on, down to scales of centimeters, and then to millimeters with different technique like scanning electron microscopy, over here with porosity maps using tritium doped polymers which are filled in this area. And then you use maybe a better radiography for measuring the tritium distribution in the soil. Or in our laboratory, another things which we do is, this is an ancient uranium mine area. So we look, for example, for trees upstream and downstream. So this is, the water comes from the top and then goes through the uranium mine. And the trees here, they have rather low levels. This is tree rings. You can look from 1900 until the year 1996, and so there's a 67 years of difference of tree rings, and you see the uranium stays about constant. But when the activity of the nuclear event happens at about 2050 or so, if there was excavation of uranium and the collection of uranium, you see that there's a quite increase of uranium in the tree rings. I wouldn't say it's dangerous, it's not my point, it's just to say there's a traceability of the human activity, which you can see also in the soil profiles. Inside you see the soil column, you see the uranium inside of this, and so on. And you combine this also with sociological studies of, for example, ancient documentation by the newspapers, and so what they talk about this area, so it's in French, I would not translate. But it's just to show that there is traces in the local history of people, in the memory also of people. So there's a question of linking memory to all of this. We need also leading edge science in this area. For example, in our place we do lots of molecular modeling, in which case we represent somehow clay minerals also by their molecules, and we have boxes of maybe 10,000 molecules, and try to see how they organize into clay minerals and how they distribute the radionuclides. Or this can be done also in cement paste and calcite minerals and so on, to find out really on molecular scale what is the mechanism of absorption by which radionuclides which are in water are bound to the surface. And if they're bound on the surface, they will somehow be not available for transport to the environment. So the question of environmental accessibility of radionuclide depends very strongly on understanding this interaction between solid phase and the aqueous phase, which is around them. Or we're working on questions of cementitious, cement waste. Cement waste is more the intermediate level waste. Here, for example, a deep geological disposal facility designed in France, and then the question is how can the gamma radiation, for example, leads to release, how is the relative humidity affects there, and what's the stability, how are radionuclides retained or not. You So we looked at, for example, also as a transport in clay rock. So we had here a clay column. We pushed water through the clay column in our laboratory and collected on the other side the quantity of water which comes out. It takes at 100 bar of pressure pump about, I think, 1 day, 1 week to get 1 milliliter through, because it's very tight material. And then you can inject some radionuclides and see how long it takes for them to come out. And here's some results. As the cesium does not come out at all, it stays fixed there. But you can then cut the column in small slices, and you see the cesium distribution in the soil. There will be no cesium released to the repository, since there's only 1 centimeter migration in 100 days. Now, on the iodine, in contrast, there is breakthrough, so we can look in the water, in the outflowing water, we find the iodine which we put in, and we can calculate from this transfer times to the environment, and for a clay rock of about 60 meters, we could say that it takes about 200,000 years to pass this barrier. There's also radiation chemistry important in this area. For example, questions of radiolytical species which are formed by interaction of radiation with the radioactive species, so get radiolytical species. We have, for example, technetium can change redox states from technetium-7 to technetium-4. We can produce these very strange molecules, or we can have oxidation of, for example, manganese by helium, or radiolytic oxidation or corrosion of uranium of steel, and so on. There are some PhD theses in this area. This goes in the wrong direction. You see here that we did this with spectroscopic analysis, which is in situ inside of this was done in a cyclotron, this experiment, and then there's some in situ analysis of the corrosion products in the cyclotron. Or we see here with autospectroscopic analysis using this spectroscopy, we see the formation from manganese 2 to manganese 4. I would not be able to describe you all the spectra, of course. And we can see then here the formation of these clusters of technetium atoms, which is a radioactive atom with relatively long half-life. And so it's very important to understand its structure, its stability in radiation field. So I have here a long list. I will not go through this whole list to avoid using up all the time on basic research needs in the area of. This could include other things like big data enabled discovery, scientific discovery. This could be in the area of instrumentation, could be in the area of new characterization methods and general integration of theoretical approaches, modeling approaches, and so on. The European Commission has launched in June this year a new project which is called EURAT-1, and this project has about 60 million euros of funding from the European Commission. So it is piloted by ANRA in France, and I'm in the project management office, and we do have then different areas here, like in CORI is, for example, cement-organic interactions, fundamental understanding of radionuclide behavior. We have spent fuel characterization. We have modeling, which is all the modeling tools, 3D modeling, and so on. Influence of temperature, the influences of gases, and so on. Then we have strategic studies, how to deal with uncertainties, or what to do with all the different types of waste in Europe, and some knowledge management in this area. And I think in Spain it is CIEMAT which is coordinating the participation of Spanish laboratories in this area. So I think about 10 laboratories are involved, and all of them somehow linked to CIEMAT as a principal party. They are linked third parties to CIEMAT. Now it talks quite a bit on science, and now we have a back thought on science. Everything gets better understood, and everything at the same time gets less good understood, because when understanding things better, you understand that the complexity is even more than you ever thought, and there's nobody anymore around which can have an overall view of all this complexity. So each one has a small view of this. So the decision maker for example, nuclear waste disposal, we would like to say yes and no. But if you have all of this coupling of chemistry and physics and mechanics and geoscience and so on, this will be difficult to not exclude an error in one of these boxes, and to find out what the error might be on the overall things. There's maybe one person to be able to respond to. So I put this question here at the same time as our scientific understanding rises, so does the complexity of the problem to describe. Does uncertainty decrease? I don't know. How to judge the adequacy of knowledge in complex systems. Little discussion on credibility of safety assessment. How to develop credibility. There's lots of questions in this area. And coming close to the end of my talk, radiological risk is something which is very difficult understood. Yeah? So there's very different opinions on this. Most of the data are collected, for example, in the bomb of Hiroshima and Nagasaki, in this area, very high doses, and then extrapolated to very low doses where people live and people are exposed maybe to nuclear events and so on. So the Chernobyl accident was maybe at 100 millisievert at some places. We're already on the high end. Fukushima is maybe much less here in this area. And average radiation, everybody gets irradiated anyhow by natural radiation. So the linear response relationship is uncertain at lowest dose, where the impact of the largest population is the highest. Depending on the use or non-use of this linear relationship, we can predict from Chernobyl, for example, 20,000 people dead, or only some few hundred. So this is not scientific uncertainties. People believe that you understand this form here better, but it's not epidemiological, it's not accessible, because the number of people you would have to irradiate at a very low dose is too high, and so this is it's not really accessible. And then you can understand the mechanism, radiation response of the cells and so on, and how to extrapolate this to the real dose. So my feeling is that the problem is also at another place. It's what I call problem framing. How are we to make sure that we understand the same thing if we talk about risk? As I said before, risk is not just a scientific term. So we say the World Health Organization developed a concept which is called daily disability adjusted loss of life years. It's essentially a reduction of life expectancy by different things, like by bad cooking habits and not ventilation, or by countries which have bad air, by bad sex. Everything is included in this daily. And so if we use this for radiation here, 100 millisievert, which I said was for Fukushima, for Chernobyl, would correspond to a reduction of life expectancy about 1 month. Yeah? And so the question poses, from my point of view, different. If I'm living in this area and I'm asked, would you like to leave because you may be one of these 20,000 people which may die later on by cancer? Probably I would say to my children and my wife, let's go out and go to another place. If I have a choice and if not the government decides for me. But on the other hand, if I ask the same question, you lose 1 month of your life, you will lose it anyhow, because even in this area, in evacuation, if you do the evacuation, you have the problem of diabetes, because the lifestyle habits change and so on. You are in an area in Japan, for example, an area where people get not anymore happy and with the children need to go to other schools and so on. So we come to an area where you lose a lot of your time just to get adjusted to a new life, and until you get adjusted, and just for certain days. I cannot answer the question because it's a personal, it's an individual question. Of course, each one has his own answer to this. But I think the question would be different asked if you're not talking about the 27,000, but just on the 49 days and so on. It's the same numbers, it's the same physics, it's just presenting the data differently. Concerning long-term policy context, nuclear legacy issues typically take decades to plan, to license, to realize, whether in treatment, in interim storage, or final disposal, decommissioning of nuclear facilities. Policies can change in few years. You just have an election. And many examples exist where the opposition of nuclear activity have permanently stopped large and complicated projects, leaving many countries without effective alternatives to reduce nuclear legacy in timely manner, so these things are just around. So the answer is always we do nothing. Phase out of nuclear energy programs in some countries have not allowed reducing nuclear legacy, example Germany. Policies for effective and long-lasting reduction of nuclear legacy need to be developed in an environment where the level of contention is high and safety evaluation extend out sometimes to millions of years, where the facts are contested and analysis itself is highly uncertain sometimes. The technical, social and political issues are complex and require an analysis of forces and conditions which resist to change. So that's why we propose, with some people, an international approach towards this to increase and to provide. The vision is somehow a new paradigm on nuclear legacy. Instead of a linear, open-ended engineering approach from concept to start to realization and potential stop and de facto standby, leading to loss of public investment and public confidence, one should go to consensus. We should have consensus as a starting point, not at the end point. We should not just start building something and later on ask permission and discussion. We should go the opposite way around. We need strong international scientific credibility by the Academy of Science, by the International Science Council, by UNESCO, and so on. Acknowledging that the non-action in this area increases the risks, increases the burden for future generations, and radioactive risk needs to be addressed by natural and social science, that engineering approaches to nuclear cleanup are ongoing since many years and will continue. But the current initiative, this initiative I'm just talking about, is to reform the science base and to do this more in collaborative international collaboration. There's urgent need to develop an innovative and operational research approach to understanding, quantification, and probable framing of radiological risk, nuclear legacy that integrates longer chains of causality. We need some kinds, to make it a small, brief statement, an IPCC for nuclear legacy. The IPCC is International Panel for Climate Change, and it has recently been used also for the biodiversity some days ago, and I think we need something in the nuclear area as well. Should be impartial, should not be like the IPCC is an intergovernment panel. We need not intergovernment here because in climate change the government they are somehow credible. In our area they are not, so we cannot base it on government. It should be some NGO type of approach. Analyzing the research, doing reporting, doing transdisciplinary research, create credibility and understanding of radiological risk and develop strategy for risk reduction, align with United Nations sustainability goals and reduce the risk of large mega project block nuclear. So here, this is the last slide, just to remember the sustainability goals of the United Nations. There's many places in this area where this type of work could fit in. I would not read this all, and I think it's just to show that it should be somehow mainstream of our society. Thank you very much.
So thank you very much for the very interesting conference. Are there any questions for the speaker?
Concerning your last transparencies, is there already some action to go to this scheme you propose of an NGO probably funded by the governments, right?
Yes, that means there's some way, but 2 years ago, or 3 years ago, we started with this initiative, and so we had some people from Stanford University, included from Harvard and so on. And We had somebody in the executive board of ICSU, the International Science Council of Science. And however, and they've supported this initiative, so this would be, they are somewhat the umbrella of all the Academy of Science in the world. So it was very strong, very strong statement. However, they merged 1 year later with the International Social Science Council to give the International Science Council, ISC. And they somehow refused to directly support the action because they are more on the level of the World Economic Forum. They would like to convince people on hunger and other things. Yeah, and this was not so high on their agenda. This was technology. We're trying to we have a meeting in this initiative in July in Tokyo to go on with fighting for this. And so we have the support of the French Academy of Science for this. So it's at least some academy. We had at the time the support of the Science Council of Japan, which is also there's some support, but the speed by which things go up is, I would say, rather viscous. It's rather not very fluid.
Why there is a difference so big between men and women in the risk of cancer and the days that you lose because of stomach of radiation?
Yes, I think there are many effects which are different. There's, for example, you have breast cancer as women is much higher probability as for men, and so if the breast is impacted directly, that's one of the effects. Now, the probability of different organs to react to radioactivity is also different. Yeah, it's also associated to this. In reality, I think there's really a large discrepancy between the radiological risk and the average risk. The World Health Organization treats all risks equally well, except the radioactive risk, which is under the work of the IAEA. They should work on this. Now, this somehow, if you take the approach of daily and you couple this in different, you have for women, for men, for each of the different cancer risks, different probability for each organ. It's different. For prostate, is for example, for men and very strong, and so there's for each for lung cancer, it's a little bit different. And there's also not only the cancer incidence, which is different. It's also the probability of dying from this cancer. So there's a difference between mortality and incident, and this difference somehow is also different. And it's different for countries. That, like, for example, in an industrial-rich country, maybe you get, for example, thyroid. There was lots of thyroid dose observed, also in Japan, but the cancer was not developed because it was found and it was controlled and so on.
So, any other question?
Thank you for your interesting talk. Besides, you had in the presentation a very important statement, how science can help into these problems. And besides the nuclear legacy existing at present from past and present facilities, it seems to me that science could help a lot looking for different decay chains in the nuclear decays after fission, leading to isotopes which are stable for in a different situation. I don't know what is the present situation with this research, and I think this will be a crucial point, you see, for the use of nuclear energy.
I think I mentioned it in the beginning of my talk. This was what you say is somehow under the name of transmutation, so that you could somehow transform one nuclei to another one, which is maybe decays faster so that it is gone earlier and so on. And there, of course, research has been ongoing since many times. But this work was largely focused on the actinides, that means plutonium, and some work was done on technetium. Nobody is able today to provide a transmutation scheme for iodine. In particular, also difficult to make targets for iodine, and because of evaporation and so on. And for cesium, that means if your cesium is one, these are some of the very toxic nuclides, and which also dominate somehow the long-term dose in many cases. Now cesium, you can destroy probably cesium-137 with some irradiation. But there's lots of stable cesium, 133. It's the same sample. So you have it's also a fission product, but it's a stable fission product. Now if you have a stable fission product which you irradiate, you may get a radioactive one. That means you actually can increase radioactivity instead of decreasing. So one could do it, why not? But in that case you would need isotope separation before, and then analyze each isotope or irradiate each isotope separately. So, and I think this was studied in France all for about, from 98, more from 91, 92, until about 2005 or so in this area. There was lots of studies in this area. And then there was also the idea to build a no-nuclear reactor, the so-called Astrid reactor was this fast breeder reactor, and sodium cooled reactor, and this concept is now somehow pushed aside. And there's not very much. There's a mirror reactor in Belgium ongoing with the idea of studying this effect by using accelerator-driven reactors with fission by accelerator, by neutrons produced by the accelerator from proton source. And so I wouldn't say that it's impossible, but at the same time, it is not something which is solved in the next 20, 30 years. And in the next 20, 30 years, there will be produced more nuclear waste. And if at that time you are able to reduce the waste by a factor of 2 or 3, then you do not gain a lot with all the waste which is already there. So you would not solve the problem. You would just make the confidence a little bit better to continue with nuclear, which produces a little bit less. So the idea of people working on this transmutation scheme is more to say we want to stabilize the production. So we destroy as much as we create. This would somehow be that you can say I'm able to make nuclear energy production without plutonium production. Not that I don't produce it, but I consume as much as I produce. So I decouple nuclear energy production from nuclear waste production. But many of these studies do not look for what happens in the nuclear reactor. That means I can produce nuclear waste without, or with little quantity, reduce the normal quantity of americium and plutonium. But at the same time, advises by increasing the level of uranium, of americium and plutonium in the fuel cycle on the sites on surface, because you need the radioactivity, you need to irradiate the plutonium to destroy, so you need a larger quantity. So it's very, very complicated.
Thank you.
Yeah, I had the same question, in fact, but I'll phrase it differently. But the natural thing, I believe, is to try and limit how much of this waste we produce. It won't take away the problem completely because we already have a lot there. How close to optimal would you say are current nuclear reactors in trying to minimize the amount of waste and the half-lives and trying to make the problem as small as possible before we even start thinking about disposal. Can we do better with thorium or with an accelerator coupled to a collider?
I think with thorium you can do a little bit better in a certain time period, but I think the decay schemes from thorium are such that after 3,000 years the difference disappears. So because the decay chains are a little bit different. Now, say you can use the EPR reactor, for example, produces a little bit less radioactivity by having a different solid water ratio to the fuel, and so there are possibilities to reduce this qualitatively, but not principally. So yeah, so it means maybe it's. I would think there's also another question. If we are in a society which invests a lot in nuclear energy, say we will go for the next 200, 300 years of nuclear fission. Why not? In that case you invest in this area and you try to optimize everything. But I calculated, for example, from the scheme of transmutation which the CA has produced, including not only what is in the waste, they can reduce americium to factor 100 without a problem, but including also what stays in the reactors over the same time period, and you add the two, you have about, in 200 years, you get a reduction of americium maybe about a factor of 2 or 3. So when you really want to reduce things, you need to have long-term vision of fission about 200, 300, 400 years. Yeah? Then it makes sense to have really long, which means, of course, you don't have only one repository, you have 2, 3, 4, 5. This would also include, and people working right now on fusion. So that means when fusion really becomes a technology, why to continue in fission? So it means, how do we have really a perspective of fission for 200, 300 years? I'm not so sure.
Well, 20 years ago, I would have had an answer to that. That was very clear. But today, people are opening the box again because fossil fuels are definitely a problem. The renewables are too late. ITER is not so rapid, not so quick as we hoped. It may be part of the manual in the end. And I guess it's hard to come up with magical bullets that really take away the problem or reduce it by 10 or so.
I agree, but I feel as well that the community which would have to defend this is not so active. That means if I see this 20 years ago, there was much more research in this area than there is today. There's still a NORA project at some place, it's still in place, but it's still a project. Yeah. And 20 years ago we had Superphoenix, we had some reactors where you could do the tests and study. Today this is not anymore the case. So I'm feeling this is possible, but it's countercurrent. Yeah.
Yeah. Somehow you seem to dismiss the importance of transmutation. I don't know, for whatever reason, but I think this is something that has to be very clear, is that transmutation has an important role, is that to reduce the radioactivity of the activates. As you said, I mean, the fission products, for the moment there is no way to make them effective. But this is very important, because this means that your geological disposal have to find solutions for, let's say, 1,000 years and not some 100,000 years. And I think that is very important. As you said, I mean, we don't have anything better at the moment than geological disposal, deep geological disposal. So I think it will be very important to continue the research in transmutation and see if we are able to do that.
I think it is, the research is continuing. Also, the European Commission is financing work in this area. So, there is work ongoing. Personally, I'm more skeptical, that's true.
Yes.
And I'm more skeptical, not because of science, because science can always move forward, but from my understanding that first, whatever you do, you need a repository, and that all studies until now have shown. And I think if you could show that's not necessary, then it's fine. But until now, there are long-lived radionuclide like cesium-135, like technetium-99, like iodine-129, and so on. And if you just focus on the actinides, there's almost, in Europe, not a single, I would say, repository project in which actinides play a key role. So in most of the repositories, whether you increase the actinide content of a factor of 10 or decrease it, the risk is the same. Now, that's a difference between... That's very provocative. That's a difference between risk and hazard potential. So that's the difference between the arsenic, which I put in the threshold in some kind of tresor and close it by the door, and some less toxic material which I leave open for my children to eat it and to die. And that means the potential is the actinides. They are the most toxic, they are the most dangerous, but they are also the most immobile. Yes. So, and risk is the probability also of being affected. So if I have a key to something and I close it, and personally I'm working on this key so that it stays down, then in this case I would not be, it would not be part, a principal risk carrier. The risk carrier principle would be iodine, selenium, and these type of nuclides which are rather mobile. And all safety analysis done in this area have shown this. So it's not, it's a little bit different in the US. In the US, they're looking for Yucca Mountain disposal, and they have oxidizing environment. And oxidizing environment make actinides very soluble. And so uranium, neptunium, and these elements, they are very mobile, and they can go into the groundwater and can be transported and so on. But you need oxidizing conditions. The European repositories are all under reducing conditions.
The ones that do not exist. I mean,
what?
The ones that do not exist. I mean, one has to find a repository for all these, which is something that is not solved. The
Which is not solved, of course, you're right. Yeah. Which is not solved, but which this transmutation is not solved neither.
No, but transmutation, the goal of transmutation is not eliminating the need of geological disposal. This is what I am trying to say.
I know, this was
not at all.
This was in France in the years of the year 90 in France. There was a law. We should study at the same importance geological disposal, transmutation of the waste, and long-term interim storage, which may help the one or the other. But they were really put alternatively. And in 2006, after 15 years of research, the conclusion was that these two alternatives are not alternatives, and whenever you do a transmutation, you still need a geological repository. So since then, if you anyhow need one, then why not building confidence on this? But you're right, there is not yet a repository nowhere, and Finland is the first one which starts to build one. And my feeling is that if you have zero actinides in this nuclear fuel, there was in the nuclear waste, there was the barriers which you need would be about the same, not entirely the same. So there's a real benefit, I should be not so negative, also for transmutation and reducing the americium inventory.
And also from the social aspect, I think it's important, because it will tell the people that you need something that will have to be stand there for 1,000 years and not for 100 years.
No, you still need
100,000
years. 1,000 years is not sufficient. Even if we have no actinides, you still need hundreds of thousands of years, even without actinides. It's not the actinides which make the long-term protection necessary. But for example, the heat, yes, if one could get rid of the cesium for a certain period, which you can separate, And then you have a special solution for the cesium, why not? And then, if you can get rid of the americium, then you can put the waste more close together, so that the environmental footprint would be reduced.
So I agree with you that we cannot leave the problem to the next generations. But on the other side, we have to make sure also that we don't prevent them to solve the problem in case that they have new resources, better ideas, and so on. So if you go for the deep geological repositories and so on, how do you guarantee this?
It's a very good question and difficult to answer, because there is, for example, in the waste certain things which could be interesting for future generations, like noble metals. There's, for example, rhodium, there's palladium in this. Palladium somehow is inactive, but for example, Areva may even think of isotope separation to get the inactive palladium out of the total palladium and so on, to get the radioactive palladium away. So these type of things are possible and should be very careful thought of. But I think we're working on this field at least 30, 40 years already, and nobody really comes up with this fantastic idea that this waste would be a resource for something extremely important. Now, of course, there's a trade-off. You can say, we leave it upstairs in our good feeling for the future generations. We leave you something which later on may be of benefit to you. So it's your choice what you do with it. But the risk is still extremely high. They have to pay this with lots of control of the environment and everything, of knowledge which needs to be generated. I'm not so sure that if I'm a future generation, and that I'm very happy with this gift. Yeah.
Okay, so we don't do any more this thing of just seal it and throw the water in the deep ocean. I mean, it's because we have learned something that is not as safe as we thought at the beginning, or is it because there is a change in society about how we perceive this risk?
There's a risk of putting it in the ocean?
Yeah. Well, it looks, a cheap option, and also, at least, for part of the waste. I would say, I don't know. I don't mean. Of course, I could, like see which are the risks, but also the people who started doing these things. So, what has changed? From this?
I think for a time period, the ocean was a solution for many waste problems and so on. But on the other hand, there have been international treaties now which exactly forbids this, because people see that this rises, for example, for the North Sea, there's a contract between all the countries living close to the North Sea, between Germany, France, and UK, and Denmark, and so on, that not a single radioactive atom should be put inside, which increases the level which is there today. This is a contract. Of course, you can change a contract, like you can change everything. But I think there were other solutions, like shooting the waste in the moon, or in the sun maybe, and burn it over there. Then definitely would. Problem is that only some of them may come back. And some rockets which you put in the sky, they may come back and burn. Take, for example, coming to your example of seabed disposal or something like this, put it in the sediments, there were some ideas. How sure are you that there's not a fish eating this waste, and then by accident you catch this fish and you are eating it?
Yeah, I agree. My question is rather, didn't we know this kind of risk, before? Or just, a question of attitude, that, years ago we were saying, okay. And now, this has changed.
I think attitude have enormously changed. And that's why I'm also a little bit against the position to accuse people of having done something with the bad people years ago. Now we know how to save the planet, and they have contaminated the planet. That's not my position. Yeah, I would definitely see there's a learning phase. For example, the sievert, which is today 1 millisievert per person per year as a threshold in the European Union, this was some 50 years much higher, the values. Yeah? And so Madame Curie, she died from using radioactivity by radium in the hands and so on. And so this learning curve somehow made us more and more, maybe we go today too much, I don't know, but I think we need a clear discussion on what is the risks which are avoidable. I'm also somehow against separating the risk from natural radiation, like from natural rocks, from granite, which has also lots of uranium, and the artificial radiation coming from the nuclear activity. This should be treated in the same way. It's the same risk, it's not a different one. So that this separation, there's lots of stigmatization ongoing. There's clubs which are building, and my acquisition, I accuse somehow both the nuclear industry and the anti-nuclear people that they keep this area in splendid isolation from all other risk areas and not putting them together, because this allows them to fight, this allows them to spend money to get their importance and so on. In reality, people should somehow work together and treat all risks, including risks of mining, risks of in the same way. And so in Germany, for example, we stopped using nuclear energy, or in the year 2022, this should be stopped. On the other hand, coal mining is ongoing, and this had been even increased, and coal mining is very well known to produce lots of other risks. So our society is not really able to discuss this in a more unemotional way. Maybe we need emotion for risk, because it's somehow linked, of course, it's our life. So we cannot take emotion away. But we should treat different risks, at least in a comparable fashion, and not forcing a country to get out of one risk to get an even bigger one on close by. So I think that my answer would be to accept the international contracts on oceans to protect them and so on. I would also, people could say, why not putting in the Antarctic? There's nobody living there. You can put there were some people saying take a non-habitated island in the South Pacific and put all the waste there. There are plenty of these options, yeah. But I think we need some control.
Okay, so if there is no other questions, and then we thank the speaker again for this very